Hello everyone. It's time for the final talk for today. And we have Seonhee Lim from Seoul National University, and she's going to tell us about dimension bound for doubly badly approximable affine forms.
Thank you very much. I'd like to first thank Anish and the organizers and everybody here. I'm impressed by all the talks here, so I hope my talk is not too bad. And since it is the last talk today, I'll try to make it leisurely and short. Okay, so unfortunately, my pointer is not working, so I have to somehow come back here all the time. But let me start from the beginning. So we all saw this week that in homogeneous dynamics, we want to approximate an irrational number by rationals. And for example, Dirichlet theorem says that for every natural number n, there exists p and q with q less than n, such that alpha minus p over q, so the irrational number that we want to approximate, minus the rational number is less than 1 over qn. And so if you multiply everything by q, then you'll have the next inequality. But this isn't just a box principle or a pigeonhole principle, because we'll have arma z as this is circle, and on this circle we'll have 0, alpha, 2 alpha, up to n alpha. So two of them will be of distance 1 over n, and which is bounded above by 1 over q. So let me denote by this double bar the distance from the set of integers. So since we have such p, the set of the distance of q alpha from the set of integers is bounded above by 1 over q. So this is what we do in homogeneous dynamics. Homogeneous Diophantine approximation. But now I want to move on to inhomogeneous Diophantine approximation. So so here we had distribution of q alpha mod integers. Now in inhomogeneous Diophantine approximation, we still have distribution of q alpha modulo z, but now we want to look at this distribution near beta. So we have a similar picture. So we have arma z, the circle, and we have alpha to alpha, etc. But we have this red point, which is beta. And so we want to know if there is some n alpha that is close to beta, the red point. So it's not exactly the same argument, but still we still have the analogous Dirichlet theorem. So for every beta, for every n, there exists this q, which is less than q, for which the distance of q alpha minus beta from the set of integers is bounded by 1 over q. And moreover, so Minkowski showed that this is actually improved to 1/4. And in fact, if you take the lim inf of this sequence as q goes to infinity, then it is 0 almost every alpha and beta. So now we can ask a similar question for matrices. So as we've seen this week, we can take this m by n matrix A, and the target vector now will be B. So this B is like a beta, and A is like a alpha above. And for these A and B, we want to find sequences of vectors Q, integer vectors in Zn. And again, for almost every A and B, lim inf of Q, power sum now, we need some power to match dimensions, which is n over m. And then again, AQ minus B, which is, so this is the real vector in Zm, right? So this double bar will mean the distance to the integer vectors Z in Zm. And it's known that lim inf is 0 for almost everywhere. And then in 2010, Bugeaud, Harrap, Kristensen, and Velani showed that for every A, now we want to gather all the B's, the target vectors, B, such that lim inf is bigger than 0. So we know that this is of Lebesgue measure 0, but we want to know whether Hausdorff dimension is full or not, and they show that the Hausdorff dimension is full. so M. So a more subtle question would be, which was raised by Uri to me, is that for fixed epsilon, now we want to look at the set of all the vectors, target vectors again, for which lim_inf is bigger than epsilon. Right? So we know that if you take the union of all these over all epsilon, then we have full Hausdorff dimension. But maybe it's true that even for just one fixed epsilon, it's possible that the Hausdorff dimension was full already. Right? So if this is not full, then the first lines, the Bugeaud, Harrap, Kristensen, and Velani's result is true in non-trivial way. So we were asking this question. So let's call this, so the set of target vectors for which for A, it is bad epsilon, epsilon bad, so bad A of epsilon. And so with Nicolas de Saxe and Maurice Shapira, we show that for almost every A, this is true. So for almost every A, for every epsilon, Hausdorff dimension of epsilon bad set for A is not full. And let me mention that Anzidler and Zhang already had shown, I think in 2011 or so, that if A is singular, then actually much smaller set, namely the intersection of all bad sets over all epsilon, is already full. So we have this extreme case of singular matrix, and we want to know what happens in other cases. So to interpret this question to homogeneous dynamics, let's do some matrix calculations. So we have this diagonal matrix. First block is e to the nt, and second block is e to the negative mt, and we have the last one number, which is 1. And then we have a unipotent element, which is block diagonal is all the identity, and above we have this n by n matrix A and the vector B, but instead of B, I'll choose negative B. And now we're looking at this at integer vectors. So let's say that my integer vector is P, Q, and 1. And if we do the calculation, we get e to the nt times aq plus p minus b, and e to the negative mt times q. Okay. So with these numbers, we want to know, we want to manipulate the previous inequality. So we want to show when this lim_inf is bigger than epsilon, but let's look at the complement. So suppose that it is, this vector is very short. Suppose that it is inside epsilon ball around 0 in RD for some p. And here I'm going to take the norm to be max of those two vectors. Yes, d is n plus 1. Thank you. Okay, so I'm ignoring this last vector, which is last component, which is always 1. So we have these two components, right? And I want to take this norm to be max of that Euclidean norm and the max of that second part Euclidean. So if the ball, it's inside the ball of radius epsilon, the first norm should be less than epsilon. And since we have some p for which this norm is less than epsilon, that if you take the double bar, so distance to the integers, then it is less than epsilon. And the second one also should be less than epsilon, so e to the negative mt times the norm of q should be also less than epsilon. So if you combine these and multiply, power n over m for the q, it is bounded by e to the nt epsilon power n over m, and the second part is bounded above by e to the negative nt times epsilon. So altogether, t part, or e to the t part, will cancel out, and we'll have only epsilon to the n over m plus 1. So that's how we get not bad vector. Okay, and moreover, let me also mention that if t is going to infinity, then by the second inequality, q has to go to infinity as well. So what we want and what we get is that lim inf as q goes to infinity of this quantity, q power n over m times aq minus b, the distance to the integer, is bounded by epsilon, some function of epsilon. Okay, so let's give some name on these matrices. So the first diagonal matrix will be our diagonal flow, AT. The second will be U, A, comma, B. And then the third, it's an integer vector, so it is in Z, m plus n plus 1. But we don't really want to think of this as m plus n plus 1 lattice. Rather than that, we want to think of it as a grid, so translated lattice. So let's ignore the last coordinate and still write it AT, U, A, B, Z, m plus n. And that will be my lattice, or actually, it's not really a lattice, it will be a translated lattice. So it lives inside SLDR semi-direct RD, mod SLDRZ semi-direct ZD. So this was in Dimitri's lecture series. This is the ASLDR, and this quotient Y is the space of unimodular grids in RD, sorry, I should have said RD. And here, by grids, we mean translated lattice. Okay, so Y is the space of grids, unimodular grids. But we still have this X, which is SLDR mod SLDZ, the space of unimodular lattices, right? So the space that I am more comfortable with. So we have this canonical projection, which is for if you have a translate of a lattice, then you project down to the lattice. And we know very well the asymptotic geometry of the space of lattices, namely, say, the origin. Something like the origin is the standard lattice CD. And if you're going to the cusp, you say that X is near the cusp, if and only if there is a very small vector inside the lattice by Malloy-Compagnie's criterion. So now let's look at the fiber. So if you have a ZD, if you have a Z2, for example, if you have Z2, you can translate Z2 without redundancy, it will be exactly by vector inside Z2 mod R2, right? So the fiber will be exactly RD mod ZD. So it's a torus, it's the standard torus. But now if you change to X, and so this X near the fiber, near the cusp, will have maybe a very short vector and very long vector. And for these lattices, if you look at how you can translate, it will be exactly RD mod this lattice, right? So if you go far off the cusp, the fiber will be still torus, but the torus will be much more long and stretched and thin. So we'll have more and more stretch and thin fiber. Okay, so now on this Y and X, the space of lattices and space of grids, we have the AT that we named, the diagonal flow, e to the nt and e to the negative mt. And the action is by linear action on RD. Okay, so now let's define something. So before I mentioned that we show that for almost every X, the Hausdorff dimension of that set, for almost every A, the Hausdorff dimension of that epsilon best set for A is full. So let me now specify what almost every means. So some lattice, so we're now downstairs, we're in the space of lattices, and we say that X is convergent on average if for every positive delta there is some compact set, K, this blue part here on the left, such that if you look at the proportion of time that we are outside the compact set, it is less than epsilon. So if you have some k for which you're taking this ratio, right? Ratio of time that we're outside blue part, so this yellow part, it is less than delta for every positive delta. And so what we really showed is that if this first theorem by Ian Rishapiran and Nicolas de Saxe is that if x sub a is convergent on average, then for every epsilon Hausdorff dimension of a best set, epsilon best set for A is not full. Okay, and so after the first theorem, we're not sure that it's true in a trivial way, so we wanted to have some example that doesn't fall into theorem, the result of theorem 1. So we wanted to have some non-singular vector, because for singular vector, we already know that the Hausdorff dimension is full. So we wanted to know that there exists some non-singular vector. So x sub a, in terms of dynamics, it's non-divergent, such that for some epsilon, Hausdorff dimension is full. And we could find such example using continued fraction. And so now the next question would be, what if x has some escape of mass on average? So we say that a lattice has delta escape of mass on average if for every compact k, now if you take the proportion of time that you're outside this k, outside this blue part, then it should be at least delta. Okay? So, and then we'll take the maximal delta possible, and then we'll say that it has delta escape of mass on average. Okay, so when n and m are all 1, so we are dimension 1, then so the corresponding lattice is two-dimensional, right? So we have just two basis vector. So if you have a very small vector, then the other basis vector will be very large. So we can use this property. And moreover, we can use continued fraction expansion for A. So, we can compute everything in terms of the best approximation. So principal convergence, which is the partial sum up to 1 over an. So let's call it Pn over Qn. And then we could show that with Bugeaud, Donghan Kim, and Michel Rams, we could show that the followings are equivalent. So the fact that we want to show for most A, so for every epsilon, dimension, Hausdorff dimension of epsilon best set for A is not full, is equivalent to limit of q sub k over 1 over k is bounded. So qk grows like exponentially. And we already know that qk is growing exponentially. If you skip 2 times, then you have to have at least 2 times the second last qk. And the third condition is that x sub a, the lattice, is not divergent on average. So if it is not divergent on average, then this Hausdorff dimension is not full. So this is true only for n and m equals 1. So what we wanted to do is to see whether this is true for arbitrary n and m. So without, yeah. Something like that, right? N 1 minus 1 over n plus n, yes. Thank you. Right, so with Uyan Kim, we show that even if you have delta escape of mass on average for some delta, which is less than 1, so if it is not divergent on average, then again, with for any positive epsilon, Hausdorff dimension of epsilon best set for A is not full for arbitrary dimension. And along the way, we could also show the dual setting. So, so far we fixed A and we collected the target vectors, right? But we could also fix B and collect all the matrices A. So we could ask this question. So A, we call A epsilon bad for B if it's the other way. So it's the same inequality, but for we want to fix B and consider A. So now we can consider this bad set for B, which is all the matrices, which is epsilon bad for B. So it's a dual problem. And we could also consider the doubly metric problem, which is considering the set of all A, the matrices, and the target vector B, for which we have bad sets, bad vectors. A is bad for epsilon bad for B. And so what I showed with Woo-Yeon Kim is that for every positive epsilon, Hausdorff dimension, actually here a little stronger result could be shown. And Hausdorff dimension of union of bad matrices for B is not full. So let me emphasize this fact by saying that for every epsilon there exists delta such that Hausdorff dimension of bad set for B is less than Mn minus delta. Okay, so I want to emphasize that this delta is not independent of B. And so as a corollary, we get the doubly metric case. So the set of all the matrices and the vectors, the Hausdorff dimension of that set is not full. Okay, so now let's go to the proof. So let's start with the proof of the first theorem by Uri and Nicolas de Saxé and myself. So the basic idea is that if you have a large Hausdorff dimension, full Hausdorff dimension, we'll get the measure of large entropy, measure of maximal entropy. So this was already used in, for example, Einstein-Lindenstrahl talk for Little conjecture, exception set of Little conjecture. But there they had absolute entropy. Here we're using our entropy relative to x. So by that we mean the relative entropy, knowing the, so given the sigma algebra of the Borel sets downstairs in the space of lattices. So B sub x is the space of the Borel measurable sets on X, the space of lattices. And we are taking the entropy relative to that sigma algebra. So now the assumption was that X is convergent on average. So what it means is that there exists some subsequence of subsequence nk going to infinity, such that if you now look at the diagonal orbit and take the average of delta measures on it, it will go to Richter limit to a probability measure, which we'll call mu zero. And now we'll use this full Hausdorff dimension upstairs. So we have upstairs we have these fibers, and we take e to the negative nk epsilon to the negative nk separated set. And since downstairs we have a probability measure and we have compact fiber, now if you look at the average of Dirac delta measure on this separated set and take all the average over the diagonal flow, then you'll still get the probability measure that we'll call mu. And this is the measure that we'll compute the entropy with. And now, so how is it related to the Hausdorff dimension? So Hausdorff dimension of this set, so this set S is actually, it's the unstable leaf for the AT flow, the diagonal flow, which is in bad XA set for, epsilon bad set for XA. And so actually the Hausdorff dimension, you can take the lower box dimension for the upper bound. So it's, which is the right-hand side. So lim inf as delta goes to 0 of log of the maximal number of delta separate sets, which I call ND, over log of 1 over delta. And we cooked up this, we took this S sub k so that this quantity is really just log of sk over nk. So now we choose increasing sequence of compact sets, exhausting Y. And then we can find some partition such that this relative entropy is bounded below by Hausdorff dimension of S minus C times some eta k, eta I. And this eta I, you can just think of it as the measure of the complement of ki. So we have this cusp part, and you can think of this as the measure of the cusp part. So this is going to 0. So we have the lower bound, which is Hausdorff dimension. Now, if you have a full Hausdorff dimension, we'll have a maximal relative entropy. So, okay. So now what is good about maximal entropy? If you have a maximal relative entropy, then it is invariant under the unipotent radical, which is in our case, it's just unstable horosphere, and which is in this case just translations. Okay, so what we could show is that if you have full Hausdorff dimension, then you have maximal relative entropy, then you have invariance for the translations. So the support of mu, which is U invariant and also AT invariant by definition, should be so the support. Okay, so support of mu is AT invariant by definition, but by this maximal entropy, it's also U invariant. So it's translation invariant, but it's not possible because if you have some lattice, then small translates cannot avoid a ball, right? So you get some contradiction to that. So the conclusion is that Hausdorff dimension is not full. So that's the main idea. So now, for the dual case and for the doubly case, so we just need to take care of the dual case. So in that case, the trick was that we have to take this L sub epsilon, which is all the grids that intersect, doesn't intersect a small ball of radius epsilon to the m over m plus n. Okay, so since we're inside the grid, this is not a compact part, right? So it's like an analog of compact part, but I mean, it's not compact, it goes to the cusp. So it's not compact, but it is closed. And so we can just switch the role of A and B. So we will have, we will switch the role of unipotent, we'll switch the unipotent subgroups. Well, we have to have some arguments before that. So we can observe that if AB is in that set, then either there exists some Q integral vector, which is for which AQ minus B is just integral. So the distance to the integral vector is 0. Or AT of XAB, so this lattice, the grid is eventually, so after some time, it will be always inside this L sub epsilon, okay, which is some closed subgroup, non-compact closed subgroup. So the second observation is that now if star is true, then if you're in this bad set for B, so this is a set of matrices, the left-hand side is a set of matrices, and there is some Q for which star is true, then it is that you can reduce to the homogeneous K, homogeneous diphoton approximation. And for that, we know that Hausdorff dimension is not full. So I think in 2013, Broderick and Kleinbach proved it. And maybe later, David Simmons had more explicit bound. Anyway, so we had a non-full Hausdorff dimension, so we can ignore this star case. So now we can just look at the second case. And then it's more or less the same argument. Except that now we have to have, so we have some mass, escape of mass on average, so we compactify the space of grids, and we switch the unstable subgroup that we want to work with. And so now we can find, as before, we can find this measure mu sub b such that the support is in L epsilon. And if you look at the measure at infinity, it is less than eta, and which is some positive number. And for some increasing sequence of compact sets exhausting Y, we have some relative entropy bounded below. But here now it's a little different from before. So before we had a relative entropy with respect to, here we had, relative to Borel sigma algebra on the space of lattices. Now here we have these U invariant measurable sets in Y, or Y hat, Y compactified if you want. But yeah, in general, I mean, by and large, it's a similar idea. So, and if you have full Hausdorff dimension, then you will have maximal entropy, so we'll have invariance. Okay, so now it's still open for A divergent and average, right? So we took care of convergent and average case, some delta escape of mass on average case, but we still have divergent and average case. And for this, we're going to use a different method. And I didn't manage to prove everything yet, but I'd like to tell you what we have. So let's say that we have Yk is a vector of best approximation. And then with Yan and Donghan Kim and Michelle Rams, we show that for A, for which A Zn plus Zn is full rank, if this Yk, so Yk is something like a Qk, right? So this denominator of the principal convergence. So if Yk, so here, so Yk is the norm of the best approximation vector small yk. So if Yk power 1 over k is going to infinity, then there is this sum epsilon such that Hausdorff dimension of epsilon best set for A is full. And this was generally, so we just covered equal weights, 1 over n, 1 over n, and negative 1 over n, 1 over n. And it was generalized to arbitrary weights by Chow, Anish, Guan, Marnet, and Simmons. Okay, so let me tell you a little bit more about best approximation. So we're looking at this infimum of ay minus p for p integral vector. And we're looking at the infimum. And so there is this sequences of yi, and the norm of yi, which is capital Yi, and the distance of ayi to the integers, integral vectors, which we call mi. And let me say that this infimum, the distance to the set of integral vectors was attained by xi. Okay, so this yi, xi are the vectors that attains the xi is the vector that integral vector that attains the minimum distance to ayi. So we can find the sequence which are local minimum, if you want. So yi is increasing, right? So we're looking at vectors, bigger and bigger vectors, for which the approximation error is smaller and smaller, right? So mi is like approximation errors, and yrs are the vectors, the length of the vectors. So yi is increasing, mi is decreasing, and m of y, so we're looking at this local minimum, which is mi. So my should be at least mi for all the y which is less than up to yi plus 1. Okay, so yi's are the length of the local minimums. Okay, so now let's get back to the matrix computation that we did. So now we're downstairs, so we have this at and ua zn. And so if you, sorry, it's m plus n, sorry. So if you look at the matrix computation, we'll have e to the t over m, aq plus p, and we'll have e to the negative t over n times q. Okay, and what is the norm of this? The norm of this is the max of these two components. So the first components will be, we're taking over all p's, so taking infimum over all p's, so the distance of aq to the integral vectors, right? The second component will be to the negative t over n times the length of the vector q. Okay, and so now, so we are denoting so that this minimum is achieved, the local minimum is achieved by xi, yi, and at that point, so we are following, we have these values, so e to the t over m, mi, and e to the negative t over n, yi. So these are the norms, okay, so these are the numbers. Okay, so we have this in mind. So now let's say that lambda 1 of x is the first minimum of lattice x. So it's like the radius of the ball where we have like k vectors of the lattice, then we'll call it kth minima. So the first minima, so it's like the minimum length of a vector inside the lattice. Okay, so now let's draw the picture of two-dimension picture. So okay. So x-axis is t, and y-axis is log of first minimum of at of xa. Okay. So what are we looking at? We have this atx, which is lattice, and for given lattice, we're going to look at the smallest vector. And we call this smallest vector xk, yk for some period, okay? So we have, so this is y equals log of lambda 1 of atxa. So this is some, I mean, it's, you have some diagonal through orbit, and this is the shortest, length of the shortest vector. And so this is attained by some vector inside the lattice, right? So some vector inside the lattice. So now we want to know how the picture is. So minimum again, so let me recall you that in the last slide, we saw that the minimum is achieved by this number, right? These are two numbers, e to the t over m times mi, and e to the negative t over n times yi, okay? So now, since we're taking log, we have to take log of these numbers. So we'll have t over m log mi, and negative t over n log ni. Right? So these are the two slopes that we see here. So for example, if m equals 1 and n equals 2, here we see slope 1, which is slope m, 1 over m, sorry. And we also see here slope negative 1/2, which is slope 1 over n. Okay, since x-axis is a t, the function of t. And so now what's the intersection with the x-axis? It's when one of these is 1, right? Because log of that is 0. So take either this equals 1 or this equals 1, then you'll have what? You'll have either 2 log yk or negative log mk. Okay? So we have these mountains upside down. We have these mountains upside down, and these points will be 2 log y1, 2 log y2, etc., etc. And these points will be negative of log of m1, m2, m3. Okay. Y minus 1/2, because so this is locally, this is the where minimum is achieved, but we have y equals log of lambda 1. So this is the like norm of the vector, not log of the norm of the vector. So we have to take the log. So mean will be t over m log mi, and negative t over m log yi. So one of these two, minimum of those. So we have either 1 over m or negative 1 over n. So I'm drawing this picture for m equals 1 and n equals 2. So we have either 1. Yeah, okay, so for me, I mean, this picture is for m equals 1 and n equals 2. Okay, so what did I want to say? Okay, so I already said that intersection with x-axis is this max being 1. And we know these t's. So now if yk power 1 over k goes to infinity, then, so we show that, we showed, and also by Anish and co-authors, showed star. So what is star? So we could put some subset of epsilon best F for A, which is actually the kind of homogeneous Differentiable approximation set. So this beta alpha of sequence yi is the space of Rm vectors for which the distance theta minus yi is bigger than alpha for every I. And so for this, there is some kind of Erdős-Taylor theorem or generalized version. And for that, we can find the low bound for the Hausdorff dimension. So when yk is power 1 over k goes to infinity, then we could find this set, beta alpha set. And that beta alpha set has a lower bound, which you can make it to go to full Hausdorff dimension. And with my other student, grad student Taehyung Kim, another Kim, we could generalize a little bit. So we don't need yk power 1 over k goes to infinity. We only need the subsequence for which it goes to infinity, but we still want another condition that for that subsequence, m times y squared is less than 1. So if you have no subsequence, then this is true trivially. It's just this distance being positive or something. But so if you take a subsequence, then you have to have this extra condition. So that's the last part that we are not being able to solve. Anyway, so the star is true, and then you can also more generally, if these two conditions are true for subsequence, then you can again find the low bound for the Hausdorff dimension, except that here we're going to replace k by this subsequence and k. Anyway, so conclusion is that, so hopefully we'll cover everything, but right now what we know is that if statistical limit of yk plus 1 mk goes to 0, then Hausdorff dimension is full. So what we mean by Lim stat, so statistical limit of ak is C if for every positive epsilon, you look at the ratio of times that is bigger than epsilon, and then it goes to 0 for every epsilon. And so we also show that if A is singular on average, then either yk power 1 over k goes to infinity, or the lower density of the times that I plus 1 mi is bigger than epsilon is equal to 0. Okay, so we have this small. So first we thought this limit is 0, then it's done. I mean, the whole question is solved, but it's only lim inf, so I mean it's only lower dimension. I mean lower density. So that's the remaining part. Okay, let me stop here. Maybe it's too short. Okay, stop here.